Hi, this is Fatimari and this is a video about how to use genetic algorithms to solve some problems. In this case, 0-1 knapsack. So the learning objectives behind this lesson are learning the concept of genetic algorithm, applying genetic algorithms to a given problem, and understand merits and limitations of genetic algorithms whenever we apply them to solve any problem. So the first question is when we can use genetic algorithms to solve any problem. So, whenever the solution to the given problem is a state and not a path, that is, it belongs to local search algorithms, in that case, we can use genetic algorithms. So, the next question is why to use genetic algorithms? So, whenever the solution is not a path but is a state, in that case, we can navigate jumpy or disconnected landscapes wherein solutions could be scattered, and this jumping or randomization can achieve solution in minimum time or in efficient way. In that case, we can use genetic algorithms. So the basic genetic algorithm follows five-step process. We start with some randomly generated states to which we call initial random population. Then we apply an evaluation function and calculate fitness value of each one of the state in the population, and we figure out which one of them are stronger. Once two steps are done, we apply selection, crossover, mutation, and thereby we get one generation. Before starting the genetic algorithms, let us understand some concepts related to genetic algorithms. The first one is chromosomes, the crossover function, and mutation. So, chromosome, also called a gene or a state, it represents the parameters which represents potential solution to the problem at hand. For example, if I have 7 elements and I'm solving some of subset problem, then for each of those 7 elements, which one of them are giving me desired sum are part of the solution. So if I represent the chromosome elements as 0 and 1, wherein 0 represents the number is not considered, while as 1 represents the number is contributing to the desired sum. In that case, the whole string of 7 elements wherein 0 and 1 are representing the element is considered or not considered is going to be a chromosome. The question would be, how do we design a chromosome? That totally depends on how do we represent a potential solution for the given problem. For example, just as I said, sum of subsets would include or exclude an element that could be represented with binary encoding. The same concept is applicable to the knapsack problem, wherein the binary representation would um, denote if the element is in or not. In otherwise, in graph coloring problem, we would be given a chromatic number, for example, 4. So 4 numbers are available with us to color, let us say 8 vertices. Then the chromosome is going to be one place for each vertex, that is 8 elements in the solution, and every element would have value from 1 to 4, wherein the number of that element would represent the color with which the vertex is colored. Similarly, in traveling salesperson problem, also it would be a permutation encoding wherein the number would represent the city, and we'll have to include all the cities as per the constraint of the TSP problem. So let us consider some example problems and what could be the possible chromosomes for them. So in the traveling salesperson problem, we have to start at the city, end with the same city, and in between the start and end of the city, we have to visit every city exactly once, and we cannot exclude any city. So these are the two constraints. So the suggested design would be permutation encoding, wherein if there are 5 cities, for example, then there would be 5 elements in the chromosome. The sixth element, though it is not given, it would be repetition of the first city. And then in between first and the n+1, because that is the last element in the city or in the root, we have to consider every city exactly once and we cannot exclude any city. So over here we have 3, 1, 5, 2, 4, wherein we can see no city is omitted, no city is repeated, and that's how the representative chromosome could be represented. Similarly, in 8 queens problem, we have to place the 8 queens on the board in such a way that no two queens attack each other in same row, same column, same diagonal. So one of the representations could be I and J values for I represents row, J represents column, and that we'll have to give for all the 8 queens. But if we go with the assumption that every queen goes in the respective row, for example, queen 3 goes in third row, queen 7 goes in seventh row. In that case, we have to give only the column number. And over here, we can repeat the column numbers because that would be not exactly a solution, but that would be a legal chromosome. So here we have an example of 8 queens problem chromosome wherein this is the place wherein the first queen goes, that is row 1 and column 4. This is for the queen 7, she goes in the 7th row and column 5 and so on. In the 0-1 knapsack problem, if we have n elements, we have to tell for all the n elements which of them are giving us the maximum profit. So here, if n is equal to 5 and if this is one of the representative chromosome, it says that first element, then third and fourth element are in the knapsack, while a second and last element are excluded from the knapsack. So this could be represented with binary encoding. So this way, the person who's solving the problem using genetic algorithms, they have to think about how they are going to represent the chromosome. Once the chromosomes are represented, in the whole genetic algorithms process, we have to use two more functions, which is crossover and mutation. So crossover is nothing but two parent genes, they cross over each other to create new offspring, and thereby they can have some characteristics of their own, one parent, and some characteristic of another parent. So this crossover, they can be of multiple types. The simplest one is single point crossover. There could be 2-point crossover. There could be 3-point crossover. There could be multi-point crossover. And how do we achieve these crossovers? So let us assume there are two chromosomes. I name them as X and Y, wherein X and Y, both of them have 6 elements in the genes or chromosome as the elements. So if I go with single point crossover, wherein I define the crossover point as 2, 6, that means first and second element of the first chromosome and 3, 4, 5, 6 elements of the another chromosome. If the single point crossover is defined as 3:6, that means first, second, third element will be of one chromosome and rest of the part of the new offspring, that is 4, 5, 6, would be from another chromosome. So we can see over here X and Y, when they are given as X1 to X6 and Y1 to Y6, with the single point crossover of 2, 6, we get X dash as X1, X2, which is first and second, and 3 to 6 are of the another chromosome, that is Y3, Y4, Y5, Y6. Same happens with Y dash, wherein Y1 and Y2 are retained, that is the first two elements are defined and rest elements are taken from the another parent. Similarly over here, in case if we are going for 3, 6 as the crossover point, then first, second and third element of their own one parent are retained and the other 3 are borrowed from other parent. Similarly, if we go for 2-point crossover, that means we have to define 2 points wherein we are going to break the chromosome and we are going to have the crossover of them. So let us see the crossover of 2, 4, 6. That means first two elements of their own, then third and fourth of the other one, and 5 and 6 of their own. So here again we have same X and Y. X dash is going to be X1, X2, the first two of their own. Third and fourth, 4 is the breaking point. So till fourth, we'll have from another parent, and then after the breaking point of 4, the rest of the elements 5 and 6 are going to be their own. Similarly, for Y as well, we take Y1 and Y2 their own. X3 and X4 are borrowed from other parent, and Y5 and Y6 are their own. And similarly, we apply 1, 5, 6 as X1, then till 5 the other parent, and 6 of their own, and so on. So this is how we can define the crossover. In genetic algorithm, every pair can have a different crossover. It's not compulsory that you should have the same crossover in the genetic algorithm process. Now let us come to mutation. So mutation brings in a random change in the parent chromosomes after the crossover is done. So these are some of the methods, very simple ones and not a complete list of how the mutation could be achieved. So sometimes they flip a random bit in the chromosome, or they choose a pair and they exchange bits in the pair. Sometimes they replace the bit in the chromosome with the lowest possible or the highest possible value randomly, or sometimes they do nothing at all. So this is how after the crossover, whenever new offspring are created, mutation function could be applied on each one of them, and some of these are given over here. So once you have understood the 5-step process, the concept of how to design the chromosomes, then crossover, mutation, let us look at the genetic algorithm, how we can represent them as an algorithm. So it takes as input the population. It takes as input a fitness function which evaluates fitness of every chromosome. So initial random population is assigned to empty set. Then after applying the fitness function, it chooses one of the strongest X chromosome, another strongest Y chromosome, and apply X and Y to create two children. And then on these children, with some random probability, we can apply the function of mutation and add these new children to the new population. And once one generation is over, we can assign this new population to population and we can repeat the loop. Now, till when we are supposed to repeat the loop? So, until some individual is fit enough to be a solution or enough time has been elapsed, till then we can go on doing this. So, the output of this is going to be an individual. The individual which is the strongest according to the fitness function is going to be the answer to this genetic algorithm. So let us look at 0-1 knapsack problem which we have been studying since long, and how can we apply genetic algorithms to solve this problem. So to define the 0-1 knapsack, we write it as given a knapsack with a capacity M and n items with weight vector and benefit vector, then the problem is to maximize pi into xi subject to the condition that summation of weights and xi's is less than or equal to m, wherein xi is 0 or 1, indicating the element is in or element is not in. So let us consider a problem instance wherein n is equal to 4, the capacity of knapsack is 10, the weight and benefit of all 4 elements are defined over here. So the step 1 is to generate a random initial population. So what do we do? Create a string of zeros and ones representing 0 is excluding the item, 1 is including the item, and just go on randomly writing for 4 places because n is equal to 4, the string of zeros and ones. Just take care that you are not repeating the exact same chromosome ever again. Each one of them has to be different, and this is just a random string of zeros and ones for 4 elements because that is the problem instance given. Now let us check as per the weight vector and benefit vector how much of the weight and profit each one of the chromosomes are giving us. And for some reference purposes, I have given them some names. So here the chromosome P has only third element N and it gives us weight of 4 and profit of 40. Similarly, this U, okay, I'll take T. It takes second and third element. So second and third element. So together the weight is 7 and the profit is 52 and so. So the next task is to use the evaluation function and get the fittest of the chromosomes for the further process. So what could be done is we can apply an easier fitness function, which is roulette fitness function. There are more of them, but this is one of the easiest one. What does it do? It computes the total fitness as a sum of fitness values of all the individuals in the current population, and then it calculates individual items fitness value, and then it will go on checking the fitness of each one of them. Now there are two things over here. One is every problem may have a different fitness function. For example, in the case of n-queens or graph coloring problem, number of pairs attacking could be the fitness criteria. The more the attacks, they are weaker chromosomes. Here, we are considering a knapsack problem wherein profit is what we are looking at and weight is the constraint. So, what could be done is fitness could be taken as profit value, while as weight as a constraint can be used to penalize the chromosomes which are violating the given constraints. So what we can do is apply them a penalty of 0 and thereby they wouldn't be considered as the part of the process. So coming here, the roulette function calculates individual chromosomes fitness value as its own fitness value divided by the total sum of the fitness. So the roulette function treats the fitness of each individual as a slice of the circular wheel, and the larger the fitness, the larger the slice, and thereby higher the probability that the individual would be selected for the next process. So coming back to our problem. So this is what we had. These are P2V chromosomes that we have considered. These were the weights calculated as per the weight vector. These are the profits calculated as the profit vector. Now, add all these profits to get the total fitness. So 40 plus 37 plus for all P2V. That gives us 220. And now, as per this formula, their own fitness divided by total fitness. That means for P, 40 divided by 220. For U, it's 25 divided by 220. And with this formula, calculate the individual fitness value. And then apply evaluation function or fitness criteria to filter out the weak chromosomes. Now, how do we decide it? It is the decision of the person who's solving the problem. How to take this decision? So actually, in reality, N would be very, very large, and in that case, some research would define how can we apply the fitness value. Just how do we decide the time quantum of round robin algorithm in operating systems? But over here, as we have taken a very small example, you can choose a value which would filter out some, not more of them, and at least we should have two pairs for the further process. So I apply 0.16 as a criteria, as a threshold, and whatever is poorer than this would be discarded. So that defines whatever is above 0.16 is passing the fitness test, and whatever is lesser than that, they are not part of the next process. So this way, in the second step, applying the fitness function, we are going to discard some and we are going to accept some. Now, in the next step, we are going to organize the ones which have passed the fitness function in the order of desirability. How do we decide this order? Here, we are trying to maximize the profit. So it goes in the descending order. If we are solving the graph coloring problem or n-queens problem wherein you are trying to reduce the number of pairs of attacking queens, in that case, the ascending values would be preferred because less attacking pairs, that means you are more close to solution, and more of the attacking pairs would be you are far away from solution. So accordingly, depending on if you are trying to maximize or minimize, the chromosomes would be organized in the ascending order or descending order of the fitness value. Here, we are going in the increasing decreasing order of the fitness value. Next process is crossover. So here we have two pairs of them. So the number is even. We can cross over R and T together and P and Q together. What if we would have had five elements or five chromosomes over here? In that case, the first one, the strongest one, generally takes part in the reproduction again. So there would have been three pairs in case if there were five chromosomes. So R and T would have been one, P and Q would have been the other one pair, and the fifth chromosome paired with R would have been the third pair. Now here, for simplicity, the crossover is chosen to be 2-4 for both the pairs, but you need not have same crossover everywhere. You can have a different one. So here, the crossover is 2-4. That means in R, 1 and 1, and is going to borrow T's third and fourth elements to make R dash, and for T, 0 and 1 and R's two value 0 and 0 would be part of T1. Similarly for P, it would be 0, 0, 0, 1, P dash, and for Q dash, it would be 0, 1, 1, 0. So thereby you create the output of crossover. So this is before crossover and this is after the crossover. Now what may happen? Some of the chromosomes after the crossover might violate the consent of fate. What do we do with them? Because still the whole process of genetic algorithms is not over, we are not going to discard them immediately. We will handle it before finalizing the output of this generation. So we reach at the final state of genetic algorithms, which is mutation. So here we have output of crossover, which is R1, T1, P1, Q1, and here we apply some of the mutation functions, and you can have same function applied to all chromosomes. You can have different mutation functions applied to different chromosomes. So there is everything depends on choice of the person who is solving this problem, and that's why if two people are solving same problem, then their outputs of the initial population, then selection, crossover, mutation might not be same. Probably at the end of the generations are over, their answers may match, but it might not match within a generation, or how many generations would they go for depending on how many points of crossover they have chosen, etc. and so on. So here in R1, we are flipping a bit. So bit C, originally it was 1, it is flipped at 0. In T1, we are swapping bits, this B and D. Right now they are 0 and 1, but originally they were 1 and 0. Then again in P1, we have flipped a bit. A becomes 1 over here, and while as in Q1, we choose to do nothing. So after mutation, the process of genetic algorithms, one generation is over, and it should give us the answer after this. So what do we do? Again, use the weight and benefit vector and calculate for each one of the chromosome the respective weights and profits, and penalize the ones which are violating the weight constraint. So here we have R1, which is weight 10 and profit is 54. There is Q1, which is taking the weight of 7 and giving us profit of 52. So over here, looking at the whole generation over here, all the four chromosomes and their weight values and profit values, it seems R1 is one of the strongest candidates right now, and thereby after first generation, profit is 54. Now, this could act as random initial population for the next generation, wherein the fitness function could be different, your criteria could be different, again your crossover, mutation, everything could be different, and this is what you are going to repeat until some enough time is not elapsed, or you are not reached to a good solution till then. So coming to the problem formulation, there are two kinds of problem formulations. One is complete state, wherein we randomly assign some or all values to the problem instance, and in incremental, we go on solving one element at a time. So I'll give you an example of, let us say, n-queens problem. So in case if I solve n-queens problem using incremental formulation, then I'll add the first queen, then the second queen. I'll check the attacks in the same column, same diagonal. Then I'll add the third queen, then fourth queen, and so on. So thereby, it's going to take a lot of time adjusting every queen. While as in complete state formulation, I'm going to add some or all queens randomly to the whole 8 by 8 board, and then I'll adjust the queens in such a way that no two queens are attacking each other in same column, same row or same diagonal. So it takes lesser of the types. So GS follow complete state formulations wherein we create a chromosome and every chromosome is a candidate solution, good or bad, but they are candidate solutions. Now, let us look at the example for the n-queens problem given in Russell and Norwin. So, each one of the chromosomes represent the column numbers of every queen. So, over here, this is a first queen goes in first row and second column. This is eighth queen goes in eighth row and second column as well. So, four chromosomes they have given. Here they have calculated by placing queens in all these positions the number of pairs of attacking queens. And finally, so sorry, number of not attacking pairs of queens they have calculated. And in total, there are 28 queens attacking each other. And now, sorry, so here goes the example of n-queens solved in the book of Russell and Norwin, Artificial Intelligence, the Modern Approach. So here they have given four candidate chromosomes wherein every queen goes in the respective row and here they have given the column numbers. For example, the seventh queen goes in seventh row but fifth column. Sixth queen goes in the sixth row and fifth column itself. So they have created random initial population of four chromosomes and they have used a fitness function of number of non-attacking pairs of queens. So by placing the queens in these positions, they have calculated how many non-attacking pairs of queens do exist. So this one has 24 non-attacking pairs of queens, this has 23, this has 20, and this has 11 pairs of non-attacking queens. Now they have used the same roulette fitness function and they are calculating the fitness value of each one of the chromosome. So 24 for the first chromosome, 24 divided by total fitness function. That gives us 31% cost of it. Then for the second one, 29% and so on. So this goes initial population. They applied the fitness function and then they are organized in the order of desirability. So this one has 23 non-attacking ones, 11 non-attacking ones, and accordingly they are organized them. So this goes selection in the order of desirability. Now here goes crossover. So here for this pair they have defined the crossover. So 3, 8, over here this is 5, 8 and so on. So for this particular chromosome, after crossover, it becomes as 327, 48552 as this one. And for this another chromosome, it becomes 247, 52411. So that's how the crossover is applied. Now in mutation, they have flipped a random bit to a possible allowed value. So here, as we are taking the column numbers as the values, we have 1, 2, 3, 4, 5, 6, 7, 8. 1 to 8 as possible allowed value for any position. So this 5 is substituted by 1. Here they have done nothing. Over here as well they have flipped bit and over here as well they have flipped a random bit to some value. And this is how they have got all the 5 stages of initial population, fitness function, selection, crossover, mutation performed, and this becomes the random population for the next generation. So, what are the merits and demerits of genetic algorithms? Good thing is that they can give a solution in linear amount of time. They have short running time because we are going with 2-point crossover, multi-point crossover, lot of randomization, etc. Memory usage depends on number of individuals, but is generally manageable in case if you look at the space complexity and time complexity. Limitation is it does not necessarily guarantee the global optimal solution because it totally depends on how good or bad is your initial population, how good or bad is your evaluation function, fitness criteria, how good or bad or how complicated is your crossover, mutation, and so on. The quality of solution depends on choosing an efficient representation, letting it run enough, long enough, and so on. So reasonably, this algorithm is simple to implement, but all the decisions are dependent on the person who's solving it, and that's what makes it a little more complex uh, methodology to solve the problem, especially if you do not have significant experience with the genetic algorithm. So these are the references. Thank you.